my research is about enabling end user and developers to make trade-off, basically about the performance of the system and make them more efficient, not only with respect to the accuracy, other factors, but also with respect to the performance as well. So today, many systems are highly configurable. Either big data engines like Storm, Spark, and other big data engines, basically robots, many different robotics platforms, and more recently, machine learning model like deep neural network. These are highly configurable. Let's look at Apache Hadoop. So I'm sure that you know much better about Hadoop than me. So if you use it before, Apache Hadoop exposed many different configuration options. For example, this single configuration option determines how many number of threads is allocated to the JVM machine. Obviously, it affects the performance, right? But this is only single out of many, and we have other, like this configuration option that's very much related to the memory consumption of the JVM machine that allocated to this machine. And different options basically have different semantics and very much related to different part of the systems. And this list is only a very tiny amount of the whole configuration space that we are dealing with. Previous empirical studies that shows that the number of configuration options has been increasing a lot over different releases. And this is very much common among other systems, either big data systems, databases, and other sort of systems. To the extent that people claiming that even all constant in your code should be very much highly configurable. So every single constant they want to be configurable. So this is important and good news for me, probably, because I'm very much interested into optimizing highly configurable systems. But let's have a look how these configuration options, that we have many of them, affect the performance. For example, in this code, this single configuration option determines whether one line of code get executed or several lines of code get executed. So obviously, most of configuration options in a way affect different performance metrics, whether it's latency, whether it's throughput, utilization, and whatever that developers and end user may concern about. For example, some may want to get very basically high throughput configuration of the system. Some other end user may like to get a configuration that consumes less, because the devices that they're deploying the system on is battery enabled. So my research is about how we can enable end user to understand the performance behavior of real world, highly configurable systems that scale well to this real world system. I show you systems, example of systems that they have 100, even 1,000 configuration options, and enable end user to reason and make trade-off based on these options that are exposed to the user. So I start this talk by giving you a very specific example and case study that I was involved, how I got to this problem, and then I'll be talking about our solution, which is based on transfer learning to enable to learn performance model for this kind of system, and a little bit of theory. I don't want to get you bored, but a little bit of theory about that. And that leads to the current work that we are doing about guided sampling, and some few thoughts about where my research is going and what I plan to do in the future. So when I was at Imperial College, I was working with a company. It was a kind of social media company. They had many customers that were interested into different contexts. So they had the social media platforms, and basically these analytics platform that they have enabled the end user to subscribe different topics that they were interested. let's review the high-level architecture of the system that they had. So they had a crawler that searched through internet, Twitter, Facebook, and other social media to get the content, and that was interested to their customers, actually. And then they stored the content to the Apache Cassandra, and they had a backend system that periodically fetched the content out of Apache Cassandra and pushed that to the content analysis that was powered by Apache Solr. And basically, the end user were able to search through this content and subscribe to the interesting content that they wanted to see. But they have a specific challenge. Their challenge was that they wanted to increase the number of users 100 times faster, 100 times more. And based on their internal analysis that they've done, they needed to increase the crawling speed 10 times faster. And also they needed to make this orchestrator real-time fetching closer to real time. So previously, it was 100K tweets per 10 minutes. They needed to increase that in order to get this pipeline more speedy for the number of users that they wanted to support. And they expected and they wanted me to solve this problem. But what they didn't want to do, obviously it was easy solution. They could increase the amount of cloud resources that they had 100 times, pay more, but obviously they didn't want to do that. And we thought, okay, probably by changing the configuration of the system throughout this pipeline, we could gain a better performance that they could support this increase of the number of users that they have. So I thought, okay, it is interesting. Let's try different configuration of the system and see what are the opportunities there. So as I show you in the overall architecture of the system, they used Apache Cassandra. Also, they used Storm and Solr. You know better than me, these different engines are very much highly configurable. They expose many different configuration options. But let's imagine they expose around 100 options, binary options. Okay? So I have a question for you. How many possible configuration of the pipeline you can imagine for this system? Any guess? Million? Actually, a little bit more. Actually, it's because these are interacting. They are integrated in a pipeline, and these different configuration options, in a way, interacting. And when we change one configuration in one engine, it very much dependent on the configuration options of the other engine down the line. So it's 200 to 300. And this is actually the number of possible configuration of the system is bigger than the possible number of atoms in the universe. So it's a lot. So obviously we cannot explore all possible configuration of the system to find the one that basically is optimal with respect to the performance that they wanted to get. But I thought, okay, let's try different, more specifically, few thousand possible configuration of the system. So each dot in this figure shows different configuration of Apache Cassandra, right? So this was the default configuration of Apache Cassandra that many companies, they stick to that. And obviously this company was using that. And you see that it is located in the upper percentile with respect to the latency and lower percentile with respect to the throughput. So it's very much suboptimal. More importantly, they have an expert, internal consultant, and that was the configuration that was recommended by the expert. Any guess what is the empirical optimal configuration among these basically few thousand samples that we got? Any guess? Should be located down there, right? So this is the optimal configuration, not obviously theoretical optimal, but empirical optimal configuration among these few thousand configurations that we have sampled. So obviously, it's much better with respect to the latency, with respect to the default configuration, as much better with respect to the throughput from the one that was recommended by the domain expert. And that was actually very similar to the other engine that it was in the pipeline, Apache Storm. So that one was the default configuration of Apache Storm, and that one was the recommended configuration by this domain expert that they had. And you see that it's very much close to the default configuration, and as you would imagine, this one is the optimal configuration of the system. So it's much better than both of these. So let's summarize what we have learned and what we have observed. So we observed that we can gain a lot better performance, more specifically with respect to throughput and latency that we observe, even 10 times, by sampling even few thousand configuration. And this is noticeably faster than the median configuration of the system. And typically, default configuration was very bad choice in these engines. And obviously, expert opinion was very much suboptimal. And as I mentioned, this is very large configuration space. Obviously, we cannot measure every single configuration of this space, because if we want to measure all possible configurations, it takes several years, basically. These measurements are very much related to the specific environment, a specific hardware version of the engine, and a specific workload that the customers or the company they had. So what happened at the end? At the end, we gained basically the objective. So they could increase support, the increase of the users that they wanted to have, and even they were able to reduce the amount of cloud resources that they had up to 20%. So that was good news for them. And actually, the tool that we developed helped them to find new optimal configuration if they basically wanted to change the workload or wanted to change the environment of the system. So for supporting this, again, the approach that I showed you was very much ad hoc. So I showed you, okay, we randomly sampled, but that doesn't work in practice for larger systems. We need to have a systematic approach for basically enabling this search. So we built a solution based on transfer learning. And before that, I need to talk about a few backgrounds. So I talk about performance model, and basically performance model is the main building blocks that enable this search through the configuration space. So what is performance model? So in this case, in the right-hand side, you see a function that shows you, okay, if this configuration options is enabled, what would be the performance? And if it is disabled, what would be the performance otherwise? So it's a simple function that maps the configuration space to some real value. And it is very useful model because it shows you, okay, in this case, the second configuration options is much more important than the first configuration options because it affects the performance much more. And also, it shows the interaction between these different configuration options. So in the case that if we enable these two configuration options, it affects the performance differently. But it's a naive and very small performance model. Obviously, we have a lot more and larger configuration space. So how we use this performance model in practice? So we have the system. We measure different bunch of configuration of the system, and we build the performance model. And we use this performance model for reasoning, for changing the architecture of the system, for optimizing, for debugging, whatever you could imagine. So this kind of model is very much useful for practitioners, software architect, and so on. So let me talk about more specifically about transfer learning in the DARPA project that I was involved. So basically, you could imagine in this case, if your system is a robotic system, you could imagine other systems as well. So this is for the presentation purposes. So she is configuring the robot, and she's sitting, configuring, and measuring the performance. So obviously, it's time-consuming. The robot may hit the wall, and she may need to reconfigure the system again and again, and it might be risky as well. If someone comes in, basically, she needs to repeat the experiment again. But in practice, we have other source of information. For example, in the robotics, we have simulators that we can measure the performance, and we gain a very similar performance of the real system without using or dealing with the real robot. So the developer can build a simulator and use this simulator for configuring the system. So what is transfer learning? So it's good that human beings are able to do transfer learning automatically. So if you play chess, I'm sure that you can play Go much easier if you didn't, comparing the case that if you didn't know. If you play football, obviously it helps you to play other games much faster. So transfer learning is an approach that basically if we gain an expertise in one domain that is very much similar to the target domain, it helps us to transfer our knowledge over the wall and help us to gain the experience in the target environment faster. And in this case, if we are able to learn a performance model in the source environment, it helps us to transfer the knowledge into the target environment and build that performance model a lot faster. So this is the approach that we're using because we observe that many companies, they use different environments that are very much similar to previous environments that they have. So maybe they change only the hardware, maybe they change some version of the libraries that they use, and so on. So the different environments that companies, they create, even it's in the continuous integration platform or so on, basically these environments are very much similar to each other. So we can gain this, transfer this knowledge that we gain in one environment to build the performance model in other environments as well. So our transfer learning is as follows. So basically, we have the simulator. We measure a bunch of different configuration of the system, and we have the real system. So obviously, the real system, as I mentioned, is very costly. So we don't want to measure many configuration in the real system. So, but we need few measurements there. And basically, our approach combines the measurements that we have done in the simulator or the source, combine it with the ones that we measured in the real system in order to build this performance model a lot faster. I don't want to really get you bored, but we have some models at the background that we used. More specifically, we use Gaussian processes because it enables us to learn a very accurate model. And more specifically, this uncertainty allows us to reason about what part of the configuration space we would like to sample. So it allows us to, for example, if we observe that this part is the highest with respect to the uncertainty, maybe it is a chance for us to explore because we may end up getting a configuration that is much better than the other observation that we have. And we can do that iteratively over time. And it is actually the main building block that allows us to do the configuration optimization. So basically, we iteratively sample the configuration space. We update the Gaussian process or GP models iteratively, and we do that over time until we exhaust the total cost of our measurements. So let's say if we have a cloud costing of 2 days, so we can use this tool to measure the system over time until our budget is exhausted. So let me give you some, talk about a little bit about the results. So this is the CMU robot platforms that we have. So you see that it's running around different corridors. Here it's more natural light, and down the corridor it's much darker. And this type of project that I'm involved is that how we can adapt these kind of robots that operate in different environments. So obviously we need to change the configuration at runtime in order to enable the robot to operate in a best possible way in different kind of environmental situation. And more specifically, with respect to the configuration space, we sample different ones. For this figure shows you different, so again, every single blue dots here represent one configuration of the localization algorithm inside the robot. So obviously we don't want the localization algorithm to use a lot of energy because this robot is battery enabled. So obviously we want to be in this part of the space, and basically we want to have a good accuracy of this robot as well. So more specifically, architecturally speaking, we have some constraints that we need to stick to that. So these space is a sweet spot for our configuration space. So we want to quickly find this high-performance configuration of the robots and swap them at runtime based on the environment situation. Also, let me quickly go through the few results. So we observed that if we want to, for example, predict the performance of the robot in the target environment, given the source environment that we already have some measurements, if we are only based on the measurements of the target environment, and since the target environment is very expensive, we cannot expect we can sample the target environment for every single configuration. So in this case, this model shows us what would be the prediction accuracy if we were able only to sample 4 configurations. So this model represents that this is very much flat, doesn't get the structure of the model that we wanted to predict. So let's say there we have 2 different dimensions of the environment. So number of particles and the number of refinement, which is related to the localization algorithm. So this is without transfer learning, and this is with transfer learning. This means that we reuse bunch of different measurements that we had from the source environment, and we can get much better model for the system that we have. Obviously, we also looked at other systems, not only robotics, but also we looked at Apache Storm, Apache Cassandra. These are different benchmarks for these kind of big data systems. And we observed that the transfer learning could help us to build a much reliable performance model for the system. And if you are interested into more details, please have a look at our paper published at SIEMS. But let's summarize. So transfer learning enables us to make trade-off between different qualities that we have. It allows us to scale to a larger space, and even it allows to build performance model if we were changing the environment. And that actually happens a lot in practice in DevOps environment. And with transfer learning, we are able to increase the prediction accuracy, increase the model reliability, and building the performance model becomes a lot cheaper. Quickly, I would like to talk about theory. So we observed that in some specific environments, we need to be careful. Transfer learning may not work in some environments that are not very much similar or are very different to the source environment. For example, in this case, we looked at different sources. Every single source, you could see that from the left to the right, the source become less similar to the target. So we observed that if the source is more similar, it helps us to predict much better models. So in this case, the y-axis shows the prediction error. But in some environments, so for example, in this environment, it works well because the prediction accuracy was, the error was a lot lower than the performance model that we have learned in the source environment. But in some environments, specifically for these environments that are very much dissimilar to the source environment, you can see the correlation coefficient down there. If we transfer the data from the source to the target, the prediction accuracy that we got was higher comparing with no transfer learning. So we need to be careful when and how to use transfer learning. So for understanding this phenomena better, we looked at different highly configurable systems. We looked at some SAT solver, video encoder, SQLite database, and we looked at SAC compiler, is a C compiler for high performance computing. These systems obviously expose many different configuration options, similar to the robots application that I showed you, and we looked at different performance metric of these. Quickly, two observations. One observation was that so the quality of the predictions is very much related to the relatedness of the source to the target. So for example, in this case, we changed the environment by changing the NUC computer on the robots. So NUC 2 means that we have 2 cores in the source, and we change it to another computer with 4 cores. So we only change the hardware, and we basically reserve the other version workload as well. And we observed that the severity is small, and this means that the source and the target are very much highly correlated, and the correlation is perfect. But when we change the, for example, the environment from cloud to the NUC machine, that was a big change, and the correlation coefficient was smaller and weaker. And also, more interestingly, when we changed altogether not only the hardware, but we also changed the version of the system and workload, the correlation coefficient was negative. This means that if we are not careful in transferring data from the source to the target, we are in bad shape. So the prediction in the target environment is a lot worse than not using transfer learning. So we observed that only, or more scientifically speaking, only in hardware changes we are able to transfer more reliably. The second observation is about some implication to sampling the configuration space. So I mentioned that the configuration space is very large. We need to be very careful with sampling. So in this case, we looked at different environments again. More specifically, look at the SAC compiler here. So the SAC compiler exposed 50 different configuration options. But we observed that only 16 of these are relevant in the source, and 10 of these are relevant in the target. So what does this mean actually for sampling? So this means that if we want to sample the configuration space, actually, out of these 50 options, many of them are not relevant. So we could simply ignore them. And we are able to understand this by having some data in the source. So instead of sampling along those 50 dimensions, we only need to sample along 16 dimensions, and it is very good because it allows us to sample more intelligently. So basically, we find a sweet spot that is a lot smaller than the whole space, and we are able to sample much better in that environment. I don't want really to get you bored, but if you are interested into that, you can look at our ASC paper for more details. But let me talk about more interesting stuff, my vision, what's going on. Software systems and very recently machine learning systems become more and more configurable. So I talked about some big data, basically robotics applications, but more recently, if you look at deep neural network, also these are very much highly configurable. Not only we can change the hyperparameters, not only we can change the depth of the architecture, but also we can change how we deploy that. And it's very much relevant to kind of application that we use every day. So if we deploy the whole architecture into our mobile devices, obviously for some image processing application, our mobile battery will run out of the battery by taking few pictures, right? Probably we need to deploy that in a hybrid environment, some part of it on cloud, some part of it on our mobile devices, or some part of it on edge devices. What I'm saying is that not only changing the hyperparameters and the design aspect of deep neural network very much affect the performance, but also how we deploy deep neural network on our devices is very much relevant and affect the performance as well. And when I talk about performance, I mean not only accuracy, but also the training speed, inference speed, that is very much relevant. Model size, obviously we cannot fit every neural network on our mobile devices, and energy consumption as well. So it's a multi-objective kind of problem you can think of. And more recent neural network looks like this. So it's very much complicated, deep, and the connection between different layers. So over time, we observe that these kind of architectures become more and more complex, and we need to have a tool in order to auto-tune that. Let's talk about applications. So for example, for fraud detection, if a company optimizes their deep neural network for a specific kind of data set that they had, as soon as a new fraud pattern is identified, this architecture is very much out of the date. So they need to find another architecture that works fine for this specific new and evolvable data sets that they find every day. This is about the number of layers for deep neural network, specific hyperparameters, and so on. But also, the way how we deploy it, as I mentioned, is very much relevant. We may want to distribute that over cloud and edge devices, but we may want to basically find a much lighter architecture and deploy everything in our mobile devices. So for example, some experimental result that we have done, we observed that if you want to distribute the neural network into the cloud, sometimes it's not energy performant because the connection that your mobile devices through Wi-Fi make with the internet, that is more energy consuming than doing the prediction themselves with a lighter deep neural network on your mobile devices. So it's very much relevant where you want to deploy this kind of model. And you may think of a very hybrid solution that split your network in one device and the rest in some other edge devices. Not only about deployment, but also you have some other stuff that you can change. So you can change even the Cypher library that you use, whether it's TensorFlow, PyTorch, whatever. So depending on your backend kind of library that you use, it may, and we observe actually that the performance also change, more specifically with respect to the energy consumption. Few results. So these are, again, each dot represent one configuration of the system. So we observed that even different configuration of this deep neural network provide different inference time. They very much provide the same accuracy. So if we choose this over this one, we get the same prediction accuracy. But which one is better? Obviously, we would like to get our prediction a lot faster. So we would like to find this or problem this or this that provide the prediction a lot faster, but the same with respect to the prediction accuracy. Or more specifically, we would like to find these Pareto optimal configuration. So again, that was the default configuration of this deep neural network. Obviously, we would like to find these 3 Pareto optimal configuration quickly. But it's not easy, right? You need to search through the whole configuration space, and slightly different from big data application. There, when you want to measure performance, you can deploy it. You can get the performance after 5 minutes, at most 10 minutes. But for deep neural network, if you want to train it on real workload, it takes sometimes 2 days for getting one configuration. So for example, for getting this result, we spent several months actually to measure these few configurations. These are very few, like less than 100. But for big data, we spent, again, several months, but few thousand. So a slight difference here. It's a lot more expensive if you want to measure different configuration of the system. So for example, this is one of the Pareto optimal configuration that is basically provide a good accuracy. Obviously, it's deep. That one provide a slightly less accurate predictions, but it's much, much faster because it's shallower, right? So for example, we would like to deploy that on mobile devices. And if you want to use that, probably we want to split that mobile devices on edge or cloud. So it's very much difficult to search through this space and find this Pareto optimal configuration of the system. So in general, what I'm conveying and very much relevant to you guys is that how we can make trade-off. And actually this model that I show you is only, the modeling part is only one step for machine learning system. So it's very much machine learning pipeline system comprising of data collection, filtering, extracting features. Learning model is only one part of it. But then we have a validation step, and also we have a model serving part as well. So for every single of these steps in our pipeline, we have many different architectural trade-off again. So the architectural trade-off that I was talking about was about only modeling. Then again, in this pipeline, we have, again, more and more architectural trade-off. And actually, in real practice, when we talk about these deep neural network and papers that you see, we only see this part. We don't see that part. So the learning part is actually very much only a small, tiny part of the whole system. When we talk about machine learning system, is a lot bigger, and it involves many different architectural trade-off. If you would like to know more about these things, I recently gave a talk for architectural practices, production-ready machine learning for the software architect. It's available on SlideShare if you want to have a look. Also, I want to quickly go through the configuration. Another type of architectural trade-off, which is very much related to production-ready systems. So this is Netflix system. A few years ago, they observed that for a few hours it doesn't work. So the customers, they complain, and they understand that there was an error in the ELB of Amazon, and that was propagated through until it hit the end users, and the whole system crashed. So this is very much relevant to configuration errors. Configuration errors actually is a very relevant problem that you see in other kind of platforms as well. For big data system and other kind of systems, a highly configurable system, when a company and organization build a system, they want to increase the number of users. So they create a configuration file that works for everyone, and basically they ship it out. But it really depends, this kind of configuration options, it really depends on the environment. Some of these options may not work in the tiny environment that SME they have. It may crash. So it's very much highly configurable systems are prone to error and crashes. And also, it's very much relevant to the architecture of the system. These are not only numbers. These are really affect the architecture, the overall architecture of the system. For example, this affects the JVM machine that is connected with the other, or some communication part, right? So every single configuration options affect different architecture relevant part of the system. So this reminds us that the configuration are software too. And actually, previous studies also shown that the configuration errors are basically a lot, happening a lot, are a major part of the overall errors of the system that they observe. And our approach is very much related what we do in research is how we can localize the error and how we can repair the error automatically by exploiting the previous knowledge of different environment that we have explored. So I'm really grateful to the collaborators, advisors, and other students that have worked with me. I'm sure that you're familiar with some of these faces. So I'm very thankful to these. So I mentioned the challenges of highly configurable systems, machine learning systems. I mentioned about our solution to do transfer learning to enable us to learn a performance model and do this architectural trade-off for the system. I mentioned that we went through and studied empirically by sampling a lot of these highly configurable systems, and I mentioned a few thoughts about where this kind of research is going, more specifically machine learning systems and highly configurable system. And thank you very much for attending this talk. So if you have a question, just go ahead. Sorry, I quickly went through a slide and I didn't give you a chance to ask. Yeah.
I have a question. So you have shown two types of configuration parameters. One were for neural networks. These are just parameters. You change them, you measure the results, and you know where you are. The other parameters, configuration parameters of Cassandra or Hadoop, are different types. So you modify them, and very often they have very critical properties, concurrency, caching, and so on. And when you change them, you find out only under very specific workloads the system begins to behave directly. So an expert knows if you touch this, it's your own risk. And if you want to really secure this against the whole configuration space and the long-term effect on different workloads, you could introduce a lot of errors that wouldn't have been introduced with maybe expert approach.
Right.
And how do you handle that?
Right. So let me rephrase that. If I understood it correctly, you mean that how you identify part of the configuration space that may result in a configuration error. Obviously, it needs expertise, right? But it's very much related to the environmental specific condition as well. So when you get some configuration right in one environment, maybe it results in a crash or in an error or in a bug in another environment because it exposed different part of the code to the system, right? Obviously, domain knowledge would help a lot to identify the part of the configuration space that is causing the error or reveals some bugs, but also experiments allow us to identify these as well. Tools allow us to identify or localize the bugs as well, because these are, as I said, very much environment specific, and the expert is, for expert, even for those who have 20 years of experience, is very much difficult to identify. They need to do experiments to identify these bugs.
Another question, if nobody else is asking. So the business case of this, Cassandra experts, Hadoop experts are already expensive. You have no replace them with machine learning experts, and I've seen this is pretty fragile, so even if I change a minor thing going from Nook to Amazon, I have to start from scratch, and that means I need this expert full time. What do you think about this?
Exactly, that's a perfect question. And that's why my research would help, because we build tools for, in order not to rely on the expert. We don't actually, in that company that I mentioned, they could easily replace the expert by the tool that we develop, because it finds much better configuration, right? So it automates the things and in a way augments the expert or end user or SMEs in order to help them to either find the optimal configuration or find a reasonable configuration that it works well for them. So it's very much relevant to this context.
To which degree are these solutions that are tailored to a specific company, or are they somehow globally valid and you can propose them for download or sell them or however distribute them?
Can you rephrase your
question? I'm thinking how to apply this now in a company. Is it so company specific that you have to enter a lot of parameters that are specific, or could you, as a business, make now the things that you should make available and sell it for a lot of money?
Exactly.
Going into also the previous question.
Exactly. So the tool that we developed, when I was at Pooyan, they were very interested to building a startup out of it and selling this tool as a service, right? That they can sell, or other companies can use this tool in order to optimize the configuration of their system. It's very much relevant because it's totally automated. It needs to attach to the end system in order to do experiments and find the optimal configuration iteratively, and it works well with different kind of platforms. I'm a researcher. I'm not very much interested in business, but these kind of things basically is very relevant to practice. So companies can use this tool as a service, this configuration optimization tool that we develop as a service. Other questions?
Is it available for free?
It's available open source, yeah, sure. It's obviously research tool. It may not be necessarily production ready, but you can get it. It's available on my GitHub. Yeah, whatever